Hello guys, I just want to show my recent SPI driver I have developed. Let me show how it is working with a small example. The problem statement is actually the slave here is Arduino and master is STM32. Whenever the slave send data, our master receive. So as we all know that slave cannot send data without the clock. So whenever the button pressed, I the master generate the clock so that as it is in a full duplex mode, whenever the clock generated by the master, slave will send the data to master. Instead of randomly sending the clock, M pressing the button. So whenever the button pressed, the master start sending the clock. So the respective data would be received. Okay. See, for debugging purpose, I'm going through this whole SP driver step by step in debugging mode. For now, for having less iterations, I will giving only the AB 2 bytes of data. Now let's go through step by step. I have done the basic initializations and enabled the SPI to interrupt. Now this it will wait here. The data available will be 1 whenever the I press button. So then only actually it will start receiving the data. Pressing the button. Yeah, now I pressed button. So whenever I press the button, actually I configure the button in interrupt mode. So the data will become 1. Actually I didn't kept a breakpoint here, that's fine. So whenever button pressed, the interrupt would rise and it will set the data available flag and it will resume the execution from where it left, that is here. Now if you can see, if you can see, as I told you, I pressed button, the data available now 1. So now start sending the dummy data. As I told, we need to send some dummy data in order to generate the clock. Then only the slave could send the data whatever it want. So whenever you're sending here, these are the basic steps we are going through. Just I'm giving the overview before going. See, first to get the interrupt, whenever the txe buffer, txe is set, we need to set the txi bit. If you can see, txi equal to 1, which will enable the interrupt whenever the txe bit set. Txe equal to 1 means whenever the buffer is free, then we can put our data into the data register, then we can send. So it is indication that whenever the buffer is free, the txe bit will set and it will raise the interrupt. In order to raise the interrupt, we have to enable the txe bit. That is step 1, which we are doing here. If you can see, we are setting the txie bit. So whenever this bit set, whenever the this is for registering the interrupt. So whenever the txe bit set, that will raise the interrupt. And the second step would be when the txe interrupt occurs, it will go to the handler and checks if it is because of the interrupt raised because of the transmit mode only. Then it will handle the whatever things need to be done in the tx mode. Now once that, okay, let's go through these two steps for now, then we will continue with the remaining. So here we said that the txe bit, so let's continue the execution. if you can see, it came to TXE interrupt handler. As now it came to interrupt handler because TXE before we never transmitted anything. So TXE bit is set to 1 only. It means we are ready to transmit our data. So what we have to do is, see, this is what I was referring. It raised the interrupt. Yes, we set the TXE bit. It will come to the SPI handler. Then here we are going to this. As our data buffer is free, what we do is, actually this is for 16 bit. If you want to store the 16 bit data, we can go through it, or 8 bit DFF, data frame format. For now I'm going through the data frame format with 8 bits. So as the buffer is free, what we can do is, this is our buffer, which is AB, not AB, sorry, the dummy data. Some random data I'm sending, that is AAA, that is stored into the data register. So once we store them to the data register, as it is free, then it will be transmitted and the clock will be generated. This transmission only for generating clock. There is no specific data we are transmitting. And once we transmitted, we should close the transmission. Closing the transmission is nothing but, there are few steps like disabling the TXE bit so that no other transmission interrupt will occur while we are transmitting. And we will inform the application that transmission has done. Okay, coming to the next steps. See, interrupt handler done. Inside that, load the data into the SP data register. We have stored the 8 bit of data, that is A, into our data register. Next byte is loaded into the data register. Now I said that we are clearing the TXE flag to not to raise the interrupt. And as we put the data during the transmission, TXE bit would be 0, just to not raise the interrupt. During the process of transmission, TXE will be 0, so that no interrupt will be raised. Now once after that, whatever the data we stored in the buffer would be shifted 1 byte of data to MOSI line. So from the MOSI, we know that MOSI line, it will send data to the slave along with the clock. Even we are not sending specific data, the clock would generate it. That clock would help slave to transmit its data. So whatever the data we had in slave, the AB, whenever the clock generated, as this is in full duplex mode, that would transmit its data. Okay, the transmission has done, the clock has generated, and now let's go through the next steps. See, the transmission has done, as I'm just showing the flow for you. Now transmission has done, clock generation has done from the master side. So clock has done. See, I will, whatever the transmission flow I have discussed, let me show you in logic analyzer so that you will get better clarity. See, this is what I am referring. I am sending 1 byte of data on the MOSI line. Till this we have done. Parallelly, whenever this clock 8 bits, 8 pulses of clock will be there for transmitting 1 byte of data. So this portion has done till now. So as this is in full duplex, At the same time, neglect this. This is for some other example, just I'm showing for reference. This portion has done. So during this clock only, on the meso line from the slave, we would receive some data, whatever we are sending. For now, we are sending AB only in this example. This is some previous example. So this we would receive when we are doing the receive thing. Now transmission has done. Let's go through the receive process, which is main. See, we are just we need to follow the same steps whichever we are done in TX transmission mode. Let's go through it. See, first it will similar to the whatever we have done in transmission, we have to do it in SPI receive data we have called, right? See, we have called this. In here we do the same steps. First we will set the RX inhibit so that whenever new data arrives into the data register from the slave, the RX ini, if we have set the RX ini, it will raise the interrupt. Now this is the thing. We have set the RX inhibit here. So whenever the RX is set, it would raise the interrupt. Now it raised the interrupt. Why? Because we already sent data from the slave, right? I showed you that AB. So it means RX ini is set, means the data is ready in the buffer, we can read. So next go through this. Once we set, it raised the interrupt. After this, now this has done. If you can see here in the register set, RxNEIE is set, and when, if you can see here, RxNE is set, so it would raise interrupt and just entered into the SPI IRQ handle. Just it is stopped at SPI. Now whatever we want to do, we can do in the SPI RxN interrupt handler. Let's go through next step. See, it entered into the RxN interrupt handler. We know inside handler what we should do. I have I have already discussed it, right? See, um, till here we are done. We set the RxN and then it would raise interrupt, and we are calling the SPI RxN interrupt handler to handle the exception. Now we just entered here. So inside that, read the data from the SPI data register. So it means now the data is entered into our data register. Now we need to read it and store in our local buffer so that we can see it. Now data has entered from meso, from slave to our data register. Now we have to read from the SPI data register. Now when we read the data, what happens is RxN is okay. We have already read then. As we have already done read, you can see. Give me a second. Hmm. We already read the data. So it became 0. That's what here it is referring. RxNE flag would clear automatically when data is read. Now the data is read. Now we are storing the received data into our local buffer so that we can see. Now again when data is received from the slave, RxNE would set again, and we need to the same interrupt handling again. Okay. Whatever the theory we have seen, let's go through the practical steps. See here we are reading from data register to we are storing into our local receive buffer. That's why that RxNA was cleared. We are reducing the buffer length. Now once we are received the data, what we should do? We have to close the reception. Closing the reception means, right? We need to clear the RxNA bit, because again we need to set, if you want to receive another byte in the send receive data receive function, we need to set the RxNE, then we will follow the process. So we are just clearing the whatever the functions we set in the, and we will inform to the application that we have received that data so that we can read it into a local buffer. Let's go through the next step. Cross reception has done. Then you can, okay, you can see here the data was received B. Actually, one iteration has done already. This is the second iteration. That's it. Again, the same process will repeat. Again, we will transmit one more dummy byte to receive the one more dummy byte, and again we receive the data from slave. Similar approach will repeat. Actually, there is small little show us there. I resolved that. Let's continue from where we, right? We sent AB. So in the first iteration we are receiving. So we got A. Actually only the read byte updated. Still the receive buffer is not stored into the receive buffer. Let's go one more step. See, now this portion has done. So the read byte A stored into the receive buffer. We can see in the debugger also. I mean in the buffer also. So the A is done, and this would fail because after AB only, here after AB only the null character will come, then only this become true and stop the execution. Now one iteration has done. See, okay, see, from this is what I want to show. Actually after closing the reception, we are intimating that this reception has done. We can store in the buffer. So I am using a callback, SPI application event callback, which will tell to the main application that the reception has done. We can store into the buffer. This is where this is where this portion has done, like storing into the local buffer. Okay, the first iteration has done. Let's go into the second one. Now the second thing, again the transmission has done. Now again the whole process actually remove the few breakpoints in the second iteration. So the same process will repeat for the second also. The same transmission will be dummy byte will be done, and the clock would generate, and the reception of one bit will come. In the reception only the whole process rx any bit again setting, again reading, again coming to the application and storing into the local buffer. Again the whole process would repeat. Okay, this is how we can do the debugging. Let's go into the running mode once rather than being in debugging. Let's run. I have run code and sent to the same ab string. Now I started. Okay, let's start fresh. Now I am pressing button. Okay, now when I press the button for the first time, I received some data. Let's see, that should be AB. Yeah, the same. We are transmitting a dummy byte. It will generate clock. A slave is already put the character A in its buffer. It is reading when this clock is happening. Same for the second time, it will read. Third time it is sending a string. This is where we check the conditional character and stop the communication. This is how the SPI works in full duplex mode. It's been very long. That's it about the